Hello, ChemComm. When we talk about ionic compounds, which we've been doing, we also spend time talking about metal reactivity, or the likelihood that a metal will react and combine with a nonmetal. Today, we'll start talking about metal reactivity trends. Let's take a look at a couple chemical reactions and see if we can find a trend. In this first reaction, we have copper that's reacting with oxygen. It turns to this black product known as copper 2 oxide. Okay, store that in your memory. The next one we're going to take a look at here is magnesium. Magnesium will also react with oxygen, and when it does, it produces this very bright white light and also gives off quite a bit of heat. And finally, we can look at gold. Gold actually doesn't react with oxygen at all. Even when you add heat, it will not react. So what we can see is that different metals on the periodic table have different levels of reactivity. And we could take copper, magnesium, and oxygen and rank them as least reactive to most reactive. The most reactive element would be magnesium because it produced heat and light. Copper turned to black, so there is a reaction happening there, and gold didn't react at all, so it's the least reactive. So we just did 3 metals, but you have an activity series reference sheet that literally ranks several metals and nonmetals based on their reactivity. If an element is closer to the top, that means it's pretty reactive, and as we move down, things get less and less reactive. If you look, things like lithium, potassium, calcium, things toward the left side of the periodic table are very reactive. And things down at the bottom, gold, platinum, silver, are closer to the midline or where the metalloids are located. The most reactive nonmetal is fluorine, and then followed by chlorine, bromine, and iodine. Those are the only 4 nonmetals you really need to know. Here's another example of the metal reactivity series and the electrons they lose when they are reacting. So the way to think about these problems is you'll be given equations and asked, will this reaction occur? One way to think about this is in terms of relationships. At the end of the reaction, the more reactive thing should be bonded. So right now, if we look at the metals we have in number 1, we have potassium and silver. On your list, you'll see that potassium is closer to the top, meaning that it's more reactive, which means it is more likely to react, and therefore this reaction is going to take place, meaning that at the end of this, potassium is going to kick silver out of its bonding relationship with sulfur. So that means potassium with a +1 charge is going to bond with silver with a -2 charge. So we crisscross and we produce K2S. And then the other product will simply just be silver by itself because it got kicked out of its relationship with sulfur. Let's look at example number 2. We have bromine. Bromine is on the non-metal side, so that means that it's going to replace another non-metal. It's not going to replace sodium, it's going to replace chlorine. And the question is bromine more likely to be in a compound than chlorine? And the answer is no. Chlorine is more reactive, and it's already bonded, which means what we would put for this number 2 is just NR. We'd put no reaction. This is not going to happen, and therefore we don't have to predict products because it's NR. So you can start to see how using this chart is really important, and it can save you some work because you don't have to predict products that are never going to form. Let's look at number 3. Pb with a +4 charge and nickel chloride. The question becomes, is lead more reactive than nickel? And the answer is no. Nickel is above lead on the chart, meaning that nickel is more reactive and it's more likely to be in a bond. And since it already is in a bond, this is NR, no reaction, will not happen. So the only time that you need to predict products is if the reaction is going to occur. Let's look at some more examples. It says use your activity series and the periodic table to answer the following questions. Will Pb metal replace silver ions? We don't have to have the whole equation. All we really need to know is lead more reactive than silver? Lead is higher up on the list than silver, and that means it's more reactive. So the answer to this question is yes. Pb is above silver and is more reactive. Question 2 asks, what trend do we see as we move to the right on a periodic table? And then it tells us to compare sodium, magnesium, and aluminum. Well, sodium is more reactive than magnesium, is more reactive than aluminum. They're all in the same period on the periodic table, so as we move right, things are becoming less reactive. We've kind of already stated this. Things on the left tend to be more reactive than as you move toward the middle. So metal reactivity goes down as you move from left to right. And then to answer this question, where are the most reactive metals? They're in the top left corner. Lithium, calcium, potassium, sodium. And then the least reactive metals would be closer to the metalloid line in the transition metals. Another problem, will iron react to a solution of lead nitrate? So we have iron, which is here, and we have lead, which it would replace, which is below it. So yes, iron would react and replace the lead and lead nitrate. Next one, will platinum metal react with lead nitrate? So platinum is below lead. So platinum would not react with lead nitrate. It would not replace the lead in that formula. Here's a question, are the least reactive metals the least expensive? And the answer to that is no. The least reactive metals down here at the bottom, silver, platinum, gold, are the most expensive. They're rare, but they're also sought after to make things like jewelry. It's much easier to wear a piece of jewelry if it's not reacting to the oxygen and the water in the atmosphere, which is why we use things like gold and platinum and silver, copper, unreactive things for those kind of materials. Other factors that could be involved and why these things are expensive is how abundant they are, how desirable they are, their strength, and how easily it is to get it out of the ground. Right now, you should really spend some time going through these equations, predicting products when necessary, and writing NR if the reaction will not happen. We'll do plenty of examples in class to make sure you're comfortable with this, but keep up the good work. We'll see you soon.